Hello students, today we're going to be continuing talking more about circles. We'll be focusing in on arcs and chords. Make sure you fill in the notes as you go. So let's first start out with a couple of definitions. The first one is what a central angle is. That is an angle whose vertex is the center of the circle. So you can get an idea here of what it looks like. You can see that the vertex here is found in the very middle where the center of the circle is, and that whole angle there is a central angle. A couple of the definitions that we have is a minor arc. A minor arc is a part of a circle that measures less than 180 degrees. A major arc is part of a circle that's between 180 and 360. A semicircle is an arc whose endpoints are the endpoints of the diameter of the circle. So what happens with a semicircle is that's where we have the exact 180 degrees. Major arcs and semicircles are named with 3 points, while minor arcs are named with 2 points. Let's do a couple of examples with this so I can show you through a diagram. So for example, a minor arc here would be AB. Since we're using 2 letters, it has to be less than 180 degrees. So our focus is going to be on this piece of the circle right here. So this is our minor arc AB. Okay, sorry about that. The second one is the major arc, which is ABD. So what you want to do is kind of like an angle, you follow where the letters are. So for this one, we'll highlight it in red. Starts at A, and we follow where B is, and we go towards D. So you see, this is an example of a major arc because it's greater than 180 degrees. The semicircle would be BAD. So in this case, again, since it's semicircle, it has to be listed with 3 letters. We're going to start, let's do this one in purple. We're starting at B, and we're working our way around towards D. So the semicircle is BAD, that piece there. It's exactly 180 degrees. You can see that that piece in the middle here is a diameter. So that's also another clue that it's a semicircle. So what we can do is find measurements of these minor and major arcs. So let's first start with our measure of the minor arc, and that's whatever its central angle is. To find the major one, you can find whatever the remaining central or minor arc is and subtract it from 360. So we'll see an example of that in about a second or so. Let's first take a look at one more postulate that we might need to use. The measure of an arc formed by 2 adjacent arcs is the sum of the measures of the 2 arcs. So just like we had angle addition postulate, we had our segment addition postulate, we also have arc addition postulate. And so what you see here is we have the circle ACB. We can find the whole measure of the arc ABC by adding the minor arcs AB with the minor arc BC, and we can find the entire arc AB. So let's kind of highlight that a little bit. So we have the minor arc AB, which is this portion right here. We can add to it that piece BC, which is this piece right here, and that's going to total the whole entire thing ABC because they're right next to each other. Our next definition here, what congruent arcs are. These are 2 arcs of the same circle, or congruent circles that have the same measure. In order for the circles to be congruent, they have to have the same radius. Our next theorem is in the same circle or in congruent circles, 2 minor arcs are congruent if and only if the corresponding chords are congruent. So what we look at here, we have this arc AB and this arc BC. We know that they're going to be congruent because these 2 chords that are formed here are also congruent. So since those are going to be congruent, these angles are going to be the same, so their arcs are going to be the same. So this is just kind of furthering showing in this specific example, arc AB is congruent to arc BC if and only if the segment AB is congruent to BC, which means the converse is also true. The next theorem we have is if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. So taking a look at a picture that goes along with this, we have a diameter. So this is our diameter right here. It is perpendicular to the chord that's formed, which is this FD right here. What that's saying here is that since this is a diameter, DE is going to be congruent to EF, but at the same time, DG and FG are also going to be congruent. So it is a bisector of the chord and that arc that follows. The perpendicular converse says if one chord is perpendicular bisector of another chord, then the first chord has to be a diameter. So this is kind of the reverse or the converse of the previous one we just discussed. So as we saw here, this chord here, since it's being bisected as marked by these things here, JK has to be a diameter. Our next theorem is in the same circle or congruent circles, 2 chords are congruent if and only if they're equidistant from the center. So let's take a look at what that might look like. So we have chords AB and chord CD. these two pieces here are going to be congruent only if we have ourselves equidistant. So the way we show that is first we have two pieces, EF and EG. They are coming from the center, and they are forming these perpendicular pieces here. So the only way for BA and CD to be congruent is if this piece has to be congruent to that piece. If that's not the case, then those two chords will not be congruent. So let's take a look at an example with all those theorems. So the first one is find the measure of an arc. So let's look at LM. LM is this portion right here. The measure of that minor arc is going to be equal to that central angle. Remember, this is the central angle right here. So these two pieces are going to be congruent, which means LM has to be the measurement of 70 degrees. Looking at MNL, which is this piece that's going all the way around, if we follow those letters, to find that, we're going to take 360 and we can subtract 70 from that. So our total is 290. Finally, looking at LMN, LMN is this semicircle right here, so it's going to be exactly half of the circle, or 180 degrees. So that's find the measure of arcs. Next one here, we want to determine if the red arcs are going to be congruent. So remember we talked about arcs can be congruent if their central angles are congruent, or if the central angles are congruent from two congruent circles. So this is in the exact same circle. Looking at the two angle measurements here, they're exactly the same. So therefore, we know that those two angles are going to have to be congruent to each other. For this next one here, same idea. We want to take a look at, is this arc DE congruent to this arc AC? Well, even though their measurements are going to be equal, so DE is going to be the same measurement of AC, they're not going to be congruent. And this is all because of this circle right here is not congruent to this circle out here because their radius are going to be different. So the answer to this would be no. So even though their measures are the same, the arcs themselves are not congruent. The next one here, we want to find the measure of arc BC, so we're focusing in on this here. What I see is I'm given the information that this chord is congruent to this chord, so what that tells me is those two arcs are congruent. So since those are congruent, those expressions can be set equal to each other. So 3x plus 11 is equal to 2x plus 48. Moving everything around, we find that x is equal to 37. Now we want to actually know what BC is, so we're going to have to take that value and substitute it back in. So 2 times 37 plus 48 is a total of 122 degrees. This is what I would like for you to do for practice right now. There is also an exit slip I'd like for you to complete, so I'm going to leave this up for about 30 seconds and I'll switch it over to the next one. Make sure you hit pause.